So yeah, let's begin. It's my pleasure to introduce Venkat Guruswamy, who is visiting us till the end of this week. And Venkat is a faculty at CMU. He has been working in many areas. So one of these is error correcting codes. This is what he's going to talk about. And he has won lots of awards, including the ECM Doxwell Dissertation Award, the Best Paper Award at IEEE Transactions, Pressburger Award, probably many more. So, and now Venkat will summarize some recent progress in error correcting codes. Thank you.
Yeah, thanks a lot, Sergei, for the introduction, and thanks to all for coming. Yeah, so this is really sort of a broad audience survey talk, so I won't get into much technical depth. It's meant to sort of give a glimpse of some different strands of coding theory where mostly biased by what things I have worked on in recent years. So, but yeah, please stop me at any point if something is not clear. Yeah, so we'll start with something just to warm up. So what is error correction about? You have some data, you send it on a channel, it gets corrupted, so that's bad. So you can't figure out what it is. So the idea is, of course, to send the data in redundant form. So you encode it by adding some redundancy to it. That gives you a code word which gets corrupted, but hopefully somehow the inbuilt redundancy allows the decoder to figure out what the data was. Hopefully that d prime is equal to d. And one point is that this transmission of data can be either in space or in time. So I could be sending a message from here back to Pittsburgh, or I could write some data on my disk today and read it a month later. Okay, and both applications are very important, and particularly the second application to storage is becoming is driving a lot of new trends also, because just of the ever increasing amounts of data which need to be stored. And just to be on the same page, so a very simple encoding scheme might be to just take maybe you're coding over bits, and then you take each bit and just repeat it 3 times, and that can correct one bit flip because you have 3 copies of a bit, so the majority will always be correct. But the problem is that's a 3-fold redundancy to correct just one error. So the question is, can we do better? And yeah, so the slide I skipped was just that codes are all around us, but this talk is about the theory. So what's a code? It's just a map which sends k data symbols to a longer string of n data symbols, let's say over the same alphabet. So geometrically you can think of these code words, which are the image, as points in sigma to the n, which are kind of very well spread out. The idea being that if you transmit a code word and there is an error, you can still go back to the original code word. Okay, so an important measure of efficiency of a code is the redundancy of a code, because you're sending n symbols, but only k of them are actual data. So n minus k of those are redundant. So as a ratio with n, that's the percentage of symbols which are redundant, and the other equally the same quantity is 1 minus tau is the rate of the code. So for example, the 3-fold redundancy, 3-fold repetition code, the redundancy is 2/3. So the idea is that you would like to keep the redundancy small while still doing the error correction as needed, and this is really the broad challenges. So in coding, whatever the noise model is, and we'll see many noise models in the talk, you can ask what is the smallest redundancy possible, which is the fundamental information theoretic limit, which allows you to correct that noise level. So that's often a purely information theoretic combinatorial question. The second question, which is more constructive, is how do you then realize this by explicit constructions of codes, which kind of come close to what is possible. And the third intertwined algorithmic aspect is that you want to use these codes efficiently, so you want an efficient method to encode and also perform error correction. Okay, so these are the 3-pronged things which one likes to study in the various models. So I said noise model, so here is a very basic noise model going back to Shannon, which is called the binary symmetric channel. So you have some probability p, and each bit which is sent on the channel is flipped IID with probability p. Okay, and so that's the pictorial depictions. When you send 0, it can get flipped with to 1 with probability p independently of the other bits. And for this, it's well known, and it follows from Shannon's work, that the best redundancy you can have is h of p, which is the binary entropy function. So when p is 0, there is no noise, you don't need any redundancy. On the other hand, when p is half, clearly the output is uncorrelated with the input, it's a random coin flip, you can't do any sensible communication, so the redundancy is 1, or the rate at which you push information is 0, and in between it is this concave function. Okay, so and this is known, and an even simpler model, which is the erasure model, is that when bits go through, they don't get corrupted, but sometimes they can get replaced by a question mark with some probability alpha. And here again, the optimal redundancy is known to be alpha, and that's clearly the best you can hope for, because when you send a long string, about alpha of these bits are going to be erased. So you must recover your data from the remaining 1 minus alpha, which means that's the best rate you can push through. Okay, and it turns out you can actually achieve this. Okay, and these are things which are called discrete memoryless channels. So this is just to set the stage for the different kinds of noise we will study. So noise we can classify along two axes. One is how the errors are caused. So in the last slide I already talked about random models where errors are caused randomly. But another model which is sort of harsher is the worst case model, where you say that, well, the channel can maybe corrupt 10% of the bits, but it can choose whichever 10% it wants in the most nasty way. And you can also have some intermediate models by posing either some computational or some information access restrictions. So that's also possible. And that's how the errors are caused, random versus adversarial at a high level. And also, what is the nature of noise? What's the different types of noise? And already in the previous slide you saw two examples. So in the bits can get flipped, so that's alteration or corruption, and that can also be done in the discrete models, or sometimes you add Gaussian noise. All those things are studied. Erasure was the second channel I showed, where some symbols just go missing. And a related model to that is deletions, where also the symbols go missing, but then you don't know where the symbols have gone missing, which makes life much worse and difficult. And there are also some more exotic models where the code words are treated as matrices and the errors are actually low rank distortions, and these actually come up in some applications. And one more important point is whether what's the alphabet? Are you coding over bits or are you coding over bigger packets? Because somehow the granularity of each symbol affects really how the error behaves. Okay, so these are all these different models, and all of these things, based on various combinations, you get tons of questions, and there's lots of these have been studied very well, and lots of progress in both theory and practice. And some of this talk I'll describe some recent results on some of these models and highlight some challenges. Okay, so that's the plan, the high level plan for the talk. So the way the talk is organized is that I have 4 different parts of the talk, and depending on time and so on, I can skip maybe one at the end. And these are roughly independent of each other, and they are basically going to tackle one of those models which we talked about, different models. Okay, we'll start with perhaps the model most friendly to the computer science audience, worst case errors. And let me warm up even more with worst case erasures, which is a very well solved problem, at least in the setting I'm going to show here. So you have a message which you encode it into a code word, and the code word has some erasures, say up to E erasures. So you would like to obviously fill in the question marks and figure out what the code word or message is. And the point is, since your message has k symbols, you clearly need at least k unerased symbols at the output, otherwise there's no chance you will get the data. So which means the most erasures you can handle is n minus k. Other than that, you just cannot fill in information. So you can ask, can you design a code which, can you get greedy and ask a code which gets this? And the answer is, turns out, yeah, we can do this, and in fact it's very simple. I'll show you the full code here, and probably all of you know this, which is you take the message. So for this it's important that sigma is big, so again the coding over big fields. So you view the message as a degree k polynomial, degree k minus 1 polynomial in kind of an obvious way by plugging in the coefficients, message bit symbols as the coefficients, and you simply do the ReedSolomon encoding, by which I mean you just take the polynomial, evaluate it at n distinct points in the field. So you need sigma to be of size at least n, and that's your output. And the point is, as soon as you get at least k unerased values, you can interpolate the original polynomial, and that gives you your data. And it doesn't matter which k symbols you get, you can always do this. Okay, so because you know which locations you get. And that's it, and that's optimal, and that solves the problem, at least for large alphabets. So now we're going to be interested in large alphabets, but what about errors? For example, let's take the same kind of code, the ReedSolomon code, and now you get n symbols, but some of these are wrong, up to E errors have happened, and you don't know where the errors are. So you can't just throw them away. So what can you do here? And the point is, if you take 2 ReedSolomon code words, because they encode degree k minus 1 polynomials, they're going to be quite far apart as code words. They're going to differ in more than n minus k locations, just because degree k minus 1 polynomial has at most k minus 1 zeros. And therefore, if you start with the code word and up to n minus k by 2 errors occur, there will be a unique sort of Voronoi region you will be in. So you can go back to the correct code word. So you can really correct up to n minus k by 2 errors, which is half the erasure bound we got. And this is, of course, this just says you can do this, but it turns out you can also do this efficiently, going back to algorithms from 1960. So many classic algorithms and widely optimized and heavily used in practice to solve this. Okay, so that's good. So now the question is, can you do better? and it turns out in one sense you cannot do better, because it's not hard to prove just by some pigeonholing argument that if you have more than n minus k by 2 errors, then you can have the situation I have there where you have 2 code words and the received word is sort of exactly within distance e of both the code words. In this case you cannot tell if you came from C or C tilde, so you cannot do error correction. So the point is, if you always want to get the correct answer, then really this ReedSolomon coding is once again the best. This is the most errors you can correct, and the way I would like you to remember this is that the redundancy of the code, which is n minus k, has to be at least twice the error fraction you correct. So you need, if you want to correct 30% errors, you need 60% redundancy. Okay, but the problem, but somehow this is very pessimistic, because the way these code words pack in high dimensional space, it's very unlikely that when you make some number of errors, you're going to go unluckily in exactly the direction of another code word. On the other hand, we do want to tackle worst case errors. So how do we sort of resolve this conundrum is a couple of ways, but one of the most popular and powerful ways is this notion of list decoding. Okay, so the idea in list decoding is that in case you're unlucky and there are more than one code word, just output the list of all code words. So again, the problem is you have this code, you want to correct a fraction row of errors, you get a noisy received word, and you kind of are promised at most row n errors have happened. So what you should be doing is look in a ball of radius rho n around that received word, output all the code words you see. And obviously the code should be kind of sparse enough in space that any such ball will not have too many code words, and also you need to somehow use the code structure to find and output these code words efficiently. Okay. And the notion itself is quite old, but it has really been revived in computer science in the last sort of roughly 30 years, starting with some work in cryptography actually. Now when, if you haven't seen list decoding before, you might say, okay, what use is the list, because I do want to recover my data uniquely. There are various answers, I don't want to dwell on it here, but one point is that typically for various natural noise models, the list will not have more than one code word, and one can prove this. And the good thing here is that you don't really need to model the channel stochastics precisely. You don't have to tailor the code to exactly the noise model. You design it for worst case list decoding, and the randomness of the channel will hopefully just mean that the list is of size 1, so you never have to deal with this issue. And of course, second point is kind of obvious, rather than just throwing the towel. If you give me a list of 3 code words, I can still maybe do something with it. And perhaps the reason why it's studied the most in the computer science literature is because it has many applications to cryptography and complexity where somehow it fits the bill exactly. Having a small list of possibilities is just as good, and that's why it's studied. Okay, okay, that's a good model, but what is it good for? So it turns out, as I said, if you want to get a unique answer always, the redundancy you need to pay is 2 times the error fraction. But turns out with list decoding, you can actually have a redundancy which is as close to the error fraction as you desire, and you can actually get this explicitly. So from work a while back with Atri Rudra, was a student at UW when I was here, and now we proved the following result, and now there are some simpler sort of cleaner proofs which get the same guarantee, which is the following. So you have a certain fraction row of errors you want to correct. You can have explicit codes with redundancy as close to row as you want, say 1.01 times row, and along with an efficient error correction algorithm, which will give you a small list of possibilities. Okay, so I've left out, the main point here is I've left out some other parameters, but the main point, it gets the trade-off between redundancy and error correction optimally. And just to remind you why this is the optimal possible, so you know that there are row n errors happening, so the channel could actually be very nice to you and even tell you that it's going to corrupt the last row n symbols and maybe just zero it out. So all the decoding you do, the only useful information you have is in the first 1 minus row fraction of symbols, which means you cannot pack more than 1 minus row n symbols. So the rate cannot be more than, basically k has to be at most this, which if you rearrange just means you need at least row n redundancy. So if the alphabet size here is big, I'll come to that in the next slide. It's something like n to the 1 over epsilon, but those things have been improved. So, yeah.
So yeah. Is there some information about how large the list is?
I'll go to come, yes. So the list will be, in this result as stated, it's something like n to the 1 over epsilon. Again, it's on the next slide, or next, 2 slides down, but those things have been improved as well. Okay. So again, for this result, yeah, since both of this discussion came up, you can make the alphabet size a constant depending only on epsilon, and the list size can also be a constant only depending on epsilon, more or less. Yeah. So I'm lying slightly, maybe if you want both of these, maybe the code will be randomized, but morally you can achieve these things. Okay. There are still some open questions left to pin down other parameters, but by and large it gets the right things. And again, so redundancy has to be at least rho for this trivial reason, because rho of your symbols could be just junk, and it turns out you can actually match it. Okay, and the code itself is just a minor variant of ReedSolomon codes. You take a ReedSolomon encoding and you do something called folding, where you just basically it's a repackaging of symbols. You take, for example, here I have shown three-way folding, where you take 3 symbols, make it a new mega symbol, and so on. So you don't add any redundancy, you just repackage symbols at the expense of increasing the alphabet size, and that's the code. In general, there are parameters m. You do m-way folding, and then there is a parameter for the decoding algorithm named s, and then you can correct this fraction of errors. It looks a bit scary, but the only thing you need to know is that if you increase s and m, you can approach tau. Okay, so if this s plus 1 by s plus 2 tends to 1, and this quantity also can tend to 1, so you can correct this fraction of errors. Okay, so that's really the code. Again, as I said, I won't go into many details, but I will just say that the algorithm itself is a higher dimensional analog of what is called the Welch-Perle-Camp algorithm, which is an algorithm to correct unique up to n minus k by 2 uniquely. So, and the whole algorithm is just linear algebraic. So there are 2 linear algebra steps, and that's the entire algorithm. And as stated, the list size this came up was kind of large. It's something like n to the 1 over epsilon, where n is the length of the code. So not very pretty. But there are many follow-ups which have addressed, once we could do a polynomial list size, there are many follow-ups which have addressed improving this. And there's some very nice connections here to pseudo-randomness, which I particularly like. In particular, a theme which comes up a lot, because these decoding algorithms are linear algebraic, they pin down the solutions to a subspace. And then there are various insights about how do you pick, how do you carefully evade subspaces and so on, which have been used to improve the list size and other aspects. And this linear algebra method is also more versatile than the previous methods. So it also works for the rank metric, where really we did not know much before these recent works came about. Okay. So that's list decoding, but really the point I want to get across is that in this three-part thing, we know the best redundancy you can get, which is as small as the error fraction, and we also have nice codes which allow us to approach that trade-off along with efficient algorithms, at least theoretically. Okay. So everything is polynomial time. So that might indicate that the problem is basically solved, or list decoding is essentially solved, but that's only the case for large alphabets. If you now insist that the coding is over bits, then the problem is wide open. So here we know that if you want to correct a fraction rho of errors, you need a redundancy not as small as rho, you need it to be h of rho, you need to be bigger than rho, but we don't know codes which achieve this. And that's perhaps one of the big open questions here. So again, going back to this thing, we know the best redundancy possible, we know the combinatorics, and that's pretty easy. You just do a simple probabilistic method, you get the answer, but we have no idea how to construct codes, or of course we don't know how to decode them because we don't know the codes. Okay. And one other thing which is still open is that we did a minor twist to ReedSolomon codes to be able to approach optimal redundancy. If you insist on ReedSolomon codes itself, the best result still is this algorithm we had with Madhu back in the late 90s, which requires redundancy which is it's slightly smaller than 2 rho, it's 2 rho minus rho square, but we don't know if this can be improved for ReedSolomon codes itself, or indeed this new twist on the ReedSolomon code was necessary. So we do not know that, and that's also a very basic question which remains open. All right, so that's it for worst case errors and list decoding. So let's move to what I started the talk with, which is binary symmetry. Any questions? Comments? Okay. So let's go back to the random flip model. You have a message, you encode it as an n-bit code word, and this binary symmetric channel flips each bit IID with probability rho, and you get a noisy word y which you would like to decode. Okay, so this is the thing. And Shannon already gave a very fine solution to this problem, in the sense that he said for any epsilon, he said that there is a coding scheme which has redundancy close to h of rho, in the following sense: if n is big enough, so you buffer enough bits, you can, in n uses of the channel, you can push through about these many bits, 1 minus h rho minus epsilon bits. Okay, And he also, and that's also the best you can do. So if you try to exceed this 1 minus h of rho, you will almost always make a mistake. Okay. So he completely pinned down what redundancy you can have. He showed that these codes exist, and also you cannot do any better. But unfortunately, as in many areas of combinatorics, the problem is this was non-constructive. He proved these codes existed, there was no structure, so the algorithms were exponential. So a natural challenge, again going back to this three-pronged structure, first question beautifully answered by Shannon, and really opened the challenge of how do you construct these codes and how do you efficiently decode these codes. Okay, and let's actually formalize these challenges a bit more formally, so to see what answer we can give. So we're going to fix a gap epsilon to optimality. We want optimal redundancy h of rho. We are going to allow extra epsilon n redundancy. So then what do we want? We want an encoding scheme mapping k bits to n bits and a decoding scheme. And again, k should be big enough so that your redundancy is within epsilon of optimality with the following properties. So, well, for all messages, if you encode it, the channel corrupts it, and then you decode it, the chance that you fail to get m is very small. Okay, let's just say it's much smaller than epsilon, just to keep it one less parameter. And the other property you want is, Shannon said that you could take n as small as about 1 over epsilon square, and we would like n to be not much bigger. Let's say it's polynomial for starters. And then we also want the encoding and decoding functions to be efficient, polynomial in n and therefore polynomial in epsilon. So the formulation I would like to use is that epsilon is a parameter which is how close to optimality or capacity you want to be, and you want a complete solution to the Shannon problem with complexity which is polynomially growing in 1 over epsilon. So that's, to me, one theoretical way in which you can pose the challenge of achieving Shannon capacity. As you get closer and closer to the limit, your overall complexity should be polynomial. Okay, and it seems like a natural formulation, and indeed there is lots and lots of work in many different kinds of codes constructed to correct errors in this binary symmetric channel model. But really in this formulation, in this form, the challenge was not answered till recent years. So there is a very simple thing you can do called code concatenation, goes back to the 60s, which can achieve polynomial complexity, but then your n needs to be rather big. Or you can keep n small, but then the complexity needs to be exponential. So either way, your complexity is growing exponentially in 1 over epsilon. And there was this great idea of LDPC codes by Gallagher, and this was revived very nicely in the mid-late 90s. Lots of beautiful results, but theoretically these codes aren't even proven to get arbitrarily close to capacity except for simple channels. So here you can't even ask this question because we don't know you can even make epsilon as close to 0 as you want. Okay, so that's a problem. And in 2008, Arikan had this remarkable breakthrough where he gave this new class of codes called polar codes, and what he proved is that in the limit of large block lengths, he proved that they do achieve a capacity, and in fact he gave algorithms which run in complexity n log n. But the reason it doesn't solve our problem as stated is that this was an asymptotic result, and there were indeed some uses of martingales in his argument which made it non-effective, at least as stated. And therefore he did not say if you want to be within epsilon of optimality, how large do you need to take n. So without knowing that n log n is useless, because if n is true to the 1 over epsilon, then that complexity is not small enough.
Why is using martingales make the bounds not effective?
Oh, because he has to apply the martingale convergence theorem, and he just doesn't know how many times you need to iterate this process before he gets close enough in some distance.
I mean, the proof of that theorem is it does give you some estimates. Anyway.
Yeah, I would love to. Yeah, in fact, I asked various people about this at some point, but turned out we had a more elementary solution. It didn't matter, but I'll be happy to hear about general, whether there's something one can do in general. So, yeah. So anyway, what we managed to do with Patrick Shea and also independently by folks at EPFL is that we gave a sort of a elementary proof which said polar codes can do exactly what is said. They can be within epsilon of optimality, and the complexity is polynomial 1 over epsilon. And this is so far the only family of codes with this particular property. And I've stated it for the BSC channel, but it extends to more general channels. In fact, it even extends to all non-binary cases as well. The non-binary cases, there are some technical challenges which are more difficult than the binary case, but those can be handled, and we can get this. And then this polynomial was not, we didn't optimize this, but it's not too bad. I think the EPFL folks cared more about the exponent, and there were some subsequent improvements, and it's not too far. It's maybe like 6 or something. Okay, now I just give some high level details similarly to the list decoding part. Again, the goal is you want redundancy h of rho plus epsilon codes. Now, so the first step is to somehow, for solving this channel coding or error correction problem, it actually suffices to solve a compression problem, and this is completely self-contained. So even if you miss some of the polar coding thing, this is a clean linear algebra problem. What do I want to do? I have a source which spits out, it's basically a binomial source. So it spits out n row biased bits, IID. So each bit is 1 with probability rho. And then it, of course, this has h of rho n bits of entropy. So you would like to compress it to its entropy, okay, which you can of course do in many ways. But I would like a compression scheme which is linear. So you need to apply a linear map m cross n, and m should be pretty close to the optimal entropy. So you should compress it to within epsilon of the optimal entropy, and the compression should be linear. And the property you need is that you need to find such a matrix H, and then this is all over F2. So all the operations are mod 2. So you need to find this matrix H and an efficient decompression algorithm such that the following property is true. You get a sample from the source, you compress it and you decompress it, you should get back the source with high probability, randomness being over the source. So if you do this, basically you can just take the kernel of this matrix H, and that will be a code which can solve the error correction problem, and that's very standard duality between source and channel coding. So this is really what is required. And a key tool underlying polar codes to achieve this is what is called a polarizing matrix. So rather than an m by n matrix which compresses, let's think of an n by n invertible matrix, which is this. So you have n bits IID at the left, and then you apply an invertible transformation. So on the left, because the bits are IID, each conditional entropy given the previous bits is the same. It's just h of rho. Okay, it's IID things. On the other hand, the polarizing matrix should have the following property. At the output, the conditional entropies should all be polarized. Namely, for most of the indices, on average, the entropy of the ith output bit given the previous bits should be either 0 or close to 1. Okay, so somehow, even though the input entropies, so it basically takes entropies which are very smeared and really polarizes them. And of course, by conservation of entropy, then of course you know that the fraction of guys which have any reasonable entropy will be close to h of rho, and the idea for compression is a natural one. If a particular index, the entropy is very, very small, then you don't send it, you just drop that bit. And that, you know, and morally that says that this bit is more or less determined by the previous things, and of course you also need to give this construction so that you can recover this bit efficiently from the previous things, but that also is what Arikon did. Okay, so first of all he proved these, you know, he gave a nice construction of this matrix A with this property along with efficient algorithms as well. So what was that matrix? So the matrix, here is the matrix, it's just the tensor product of this 1101 m times, so that's it, it's as explicit as it gets. And so I won't prove the polarization, but just to give you a taste of what happens for 2 by 2 case, this is essentially the only interesting matrix 1101. So what happens? U1 is x1 plus x2 and U2 is x2. Now unless x is already at one of the boundaries, namely it has entropy 0 or 1, the sum of 2 IID copies of x will have more entropy than x, and therefore the conditional entropy of U2 given U1 must be less than h of x, because the sum of the two things is 2h of x. So what you have done is you have taken two equal entropies and you have done a linear transformation and split them, one going higher and one going lower. And really what this tensor product does is that if you analyze it carefully, it's basically doing this in a recursive way, and basically the entropy gets driven further and further apart till it settles down at ones and zeros. Okay, that's at a very high level what Arikon proves. Okay, and specifically what Arikon proves is the following thing. He gets optimal compression in the limit, namely the fraction of indices which have sizable, you know, conditional entropy is very, you know, is what you would expect. Only h of rho of the indices at the output have any entropy at all, the rest have very low entropy. So you drop those, you get optimal compression in the limit. And what we prove is basically a speed of convergence result. So we prove that if you want to be within epsilon of this limit, it suffices to take n to be at most poly 1 over epsilon.
Is the degree known?
Oh, the degree, no, we don't know the optimal degree. As I said, you can be careful and make it like something like 1 over epsilon to the 6. And there is, I don't know how rigorous the proof is, but there is belief that it's not better than 3.5 or something. So, but it's not completely known. And really the core step which one needs to analyze is that if you have a random variable z and you take two IID copies of this, how much will the entropy increase? You need to quantitatively estimate this, and that's the key to getting these quantitative. Okay. And these questions become harder in the prime case, general prime case, and we don't have very good answers. We did something ad hoc to prove a similar result, but the bounds are pretty weak. Yeah, and I'll be happy to tell people offline if they want to go. This is a very clean sort of entropy sumset inequality type question lurking underneath this. Okay, so that's the polar coding thing. So, okay, any questions about this? That's all I want to say. Okay, so now let's talk about deletions.
So just a quick question. Do you prove something new for this last question, or do you use something that was known?
Oh, for this thing?
Yeah. No, the last one for
entropy. Oh, for entropy, we prove something new. Yeah, yeah.
So what is the condition exactly that you have on Z?
So for example, so z could just be, usually z is a conditional random variable. That's what is needed for these applications. But a simpler question is you could just take z to be some random variable on z mod p, integers mod prime.
Okay.
And you can ask what is the minimal entropy increase you can have. Right. And of course, assuming it's not at the boundary. Of course, if z is completely random, then there is no entropy increase. If z is uniform, is deterministic, there is no entropy increase. But let's say it has entropy rate like around half. How much is it guaranteed to increase? So you need to understand. Okay, and what we prove is that there is always a finite increase. So we prove that it increases by at least 1 over p or something, and that suffices for this application. But I don't know what's the worst z, which increases the least.
It's like 1 over p times the gap between...
Yeah, so you quantify it, you take this and you divide it by something like h times 1 minus h.
I mean, it would be natural, if the entropy is half, it would be natural to say that it's uniform on 0 to root p, something like that.
Exactly, yeah. So that's an upper bound. But we prove something much weaker than that. Yeah. So that will, in some normalization, have the entropy increase by 1 over log p. We only prove it increases at least by 1 over p square or p cube, or maybe even slightly worse.
Or the worst case is like arithmetic progressions or something.
Well, that's exactly.
Yeah, that was my intuition. But then at some point I asked Ben Green this question, and he felt maybe some discretized Gaussian might be worse, and I don't know. So I haven't given it enough thought. But it's a nice question, and of course it relates to, in the arithmetic combinatorics world, what's set z for which z plus z is as small as possible. I think this is the entropic version. And actually the Tao Wu book actually has an entropy version thing, but it's some sort of deleted scenes. It didn't make it to the book, but if you can find it online somewhere. Yeah.
So you recover it from
Yeah. But I think this particular form is not. And this has been studied for integers as well. For if z is supported on integers, then, and in fact any torsion-free group, there's a precise answer no. But not for finite groups. All right, so deletions. Okay, let's see.
This we like over here.
Yeah, I know. So I think I have two more acts. One is deletion and one is erasure. So, and there are people liking both of these. We'll see. Let's talk about deletions. Okay, what's the deletion model? This is yet another model, which is, very classic. But there's a lot of renewed interest in this because of ostensibly applications in biology. But, for this audience, there are very nice math questions here. So you have an n-bit, n-symbol string. S of these symbols get dropped, so you get a subsequence. Okay, so two examples. So it can be over bits or it can be over larger alphabets. So basically, receiver gets a subsequence and doesn't know where the bits have gone missing, which makes recovery a major headache, because compared to where you lose all synchronization. So very standard classical techniques seem to break down. In particular, a lot of techniques around revolving around linear codes or algebraic codes don't seem to apply. You need to really sort of think afresh, it seems. Okay, so again, the goal is you want to design a careful code such that no matter what code word you send, you can uniquely recover it. And here I'm only talking about two things. I'll say I'm only going to talk about unique decoding, and I'm going to talk about worst case deletions. So, okay, so the channel can delete any S symbols of its choice, and I want to get a unique answer. So I want a unique C, which you can get from just its subsequence. Equivalently, you just want the property combinatorially that if you take two distinct code words, their longest common subsequence should have length less than n minus s. Because if they had a common subsequence of length n minus s, you could send that, you could receive that, and you don't know if you got C or C prime. Okay, so that's the property. So it's basically distance, but not in the Hamming metric, but in this Levenstein or edit distance metric. And what is sigma? So if I allow sigma to grow with n, then one trick I can do is, like, this is the packet header trick used in the internet. I can just tag each symbol with its location, and then deletions just reduces to erasures, which I know how to solve, like I showed a few slides back with ReedSolomon Codes. But the model is very challenging when sigma is fixed, and let's focus on really the most basic case, which is 0, 1. So when you send bits. Okay, again we have a three-pronged question. So you can say, okay, suppose I delete p fraction of bits. What's the best redundancy I can have? Can I construct codes? Can I decode these? The first question itself is open. Okay? So even the first question is unanswered, and as I will see, even much easier things than this are unanswered. So again, let's go back to this specific question. You have bits, and the adversary deletes pn of these bits adversarially. So you must be able to decode the original n-bit code word from a received 1 minus p, any sequence, subsequent, any of its subsequences of this length. Okay. So clearly, as p increases, you get shorter and shorter subsequences. You can't do, life gets harder. So you can ask, okay, what's the best code you can have as a function of p? Hopeless, at least currently. So let's make a simpler question. Can you at least tell me what is the largest p for which I can have a non-trivial code? And what's the non-trivial code? A code for which the rate is bounded away from 0. Okay, so equivalently, the code has size at least exponential in n. Okay, so that my redundancy is bounded away from 1, the rate is bounded away from 0. Okay, so this is the question. Okay, can we answer this? It turns out even this is not known. So let's see what's the story here. So again, that's the question. What's the largest deletion fraction you can hope to correct with a non-trivial code? Now certainly p is less than half. So you cannot correct 1/2 deletion fraction. Why is that? Think about it for us in a minute. You will realize the adversary can do what it wants. So it can just scan the code word for all zeros or all, it can either delete all the zeros or all the ones. And one of these will occur at most n over 2 times. So the adversary can basically make sure that you always get one of two possibilities, either 0 repeated n over 2 times or 1 repeated n over 2 times. You can only push one bit of information through regardless of how many bits you send. Okay, that's a very trivial limit. Just trivial proof. Now the question is, okay, that's the only limit I know really. So can you correct a deletion fraction approaching half? We do not know this, which is a bit striking.
Like for binary errors, it's a quarter.
Binary errors, it's a quarter. Binary erasures, it's half. Yeah.
Yeah, but that should be harder than.
It should be harder than errors. Okay, that's what Sergei says. Let's see. Okay, so what was known before, till recently, even non-constructively, basically you could take a random code and do the usual thing. The largest deletion fraction known to be correctable was around 17%. And this comes from the expected length of longest common subsequences over n-bit strings, which is an unknown quantity, but using known bounds, you can get this. Okay, that was the story. And again, half was the limit, and this is what you could do. And what we showed last year was that you can actually correct a deletion fraction approaching 0.414 square root 2 minus 1, which incidentally exceeds 1/4. So it's actually in an odd way, it's easier model than bit flips. And not only do we, and we actually give these codes. So we construct these codes along with an efficient deletion correction algorithm. Okay, so it's not just an existential result, but even existence wasn't known before. Okay, and I'll at least try to roughly sketch the construction for p less than 1/3, which is quite clean and easier, and then additional ideas go into this, which I won't get into. Okay, so that's what I want to spend a couple of slides on. So how do we do this? The idea is really to concatenate, because somehow directly working with bits is difficult. Deletions are a bit easier to cope with when your symbols are bigger. When they're really big like n, it's trivial. But when they're modest, like a big constant, you can still do something good. For example, you can take the alphabet size to be some polynomial in 1 over epsilon, and you can correct a deletions approaching 1. Okay, and you can do this just by picking a random code, or you can even do these. We managed to do these things explicitly with reasonable exponents. And then the idea is that you take these symbols from 1 through k, and you re-encode them as bits. And here is where you have to do some things which are different. And the way we do this for this construction is that we basically encode them by alternating zeros and ones, balanced strings, but the run lengths between these different strings vary quite a bit. They increase geometrically. And somehow the idea is that if you say look at the bottom string and the top string, they don't have a long common subsequence. Just because this string has a whole run of zeros, so if you want to match it with this, you have to alternate, you have to lose every other symbol there. Okay, so I'll come to that in a second. And we prove that this resulting code has the property that no two code words have a long common subsequence of length 2/3 or so, or equivalently it can correct deletion fraction approaching 1/3. Okay, so that's the thing. So this, yeah, and it turns out you can also get an efficient algorithm, but that at least currently is a bit of a hack, and we combine it with some ReedSolomon ideas and exploit its list decoding. So I'm not going to say anything more about that, but just to point out that this primitive of list decoding connects up to many other parts of coding as well. It's a useful primitive even if you don't care about list decoding itself. Okay, so okay, and why this 1/3 comes, at least let me sketch the limitation of the construction, even if I don't prove it actually has the property. Suppose you have these symbols A, B, D from these big code word, A, B, C, D from this bigger alphabet, and you encode it by these oscillating strings. So what you can do is that you can take any string here and you can actually completely match it with two copies of the string, because that string maybe alternates with low frequency. So you can always match the zeros with all the zeros here and the ones with the ones here. And then you might get the other pattern there where this is a lower frequency thing, and then you can map it like this. So you can have such an interlocking pattern, right? And then what you have done here is that you've got a common subsequence of length equal to 2 blocks in a chunk of 3 blocks. So your LCS is about 2/3, and somehow that's, we cannot get past this for this construct. Okay, and more or less we show that this is close to the worst case, and that's how we show this is the worst thing which can happen, and so we get 1/3. A little bit more detail, one useful notion we work with is this notion of a span. Suppose you have two sequences W1 and W2 and you create a common subsequence, you can ask what is the smallest contiguous string which contains sigma, so that must be somewhere, and you simply sum up the lengths. That's called the span of this sigma with respect to these things. Intuitively it's a measure of how costly is it to create sigma, right? So it's a cost measure of, so clearly the span is like at least twice the length of sigma, because you need to find sigma in both of those. But if it's much more than twice, then it's somehow you're paying a bit of price to get a common subsequence like sigma. And somehow the reason for this particular choice we make of these oscillating strings is the following lemma, which is elementary to prove, which is that if you have two sequences, let's say infinite sequences which oscillate at different frequencies A and B, and you make a common subsequence, then as soon as, if any long enough sequence basically has a span which is almost 3 times. So basically if the frequencies are very different, then the span of a subsequence is almost 3 times the length. You need to pay 3 times the price rather than twice the price. And why is this related to LCS? Because the span of any sequence, so if you're talking about a sequence created from length n sequences, the span is at most 2n, because you're just creating it as a common subsequence. On the other hand, it's at least the length of 3 times the length of sigma. Putting those two together, the length of sigma is at most 2n by 3. Okay, so this is a very rough sketch, but really the main point is you analyze how costly is it to create a subsequence relative to the length of that sequence. And for these oscillating strings, that ratio tends to 3, and that's what gives you the 2/3. Okay. And the square root 2 minus 1 comes because we give another construction where the ratio is basically 2 plus square root 2. Okay, and that gives you, it's like 3.414, and then that gives you the better result. Okay. Again, let me remind you this basic question which is still open. We still do not know if you can correct a fraction of errors, which is 0.49. Okay, that remains open. And now let me just have this one slide which I added last night, just to point out some recent work. Just this question really bothers me, and I don't know which way to bet. Initially, I was sure you shouldn't be able to do 1/2. And maybe I still lean towards that belief, but I'm not sure anymore. But to get some idea on this question, we looked at some other models. So what are some other models? We can ask about random deletions. Each bit is deleted IID with probability P. So in this case, it turns out you can actually handle P tending to 1 with rate bounded away from 0. This was was known by Drini, Mitz and Marker more than 10 years back, maybe even before that. I'm not sure if that's the earliest reference. And we can also now get these things explicitly, so that's fine. But this is random deletions, and we don't understand adversarial deletion. So just to get some foothold, we looked at some intermediate models. So there are 2 models we considered. One is the oblivious model, where the deletion pattern is arbitrary, but it's picked before you see the code word. So you sort of swap the quantifiers, and this is clearly weaker than adversarial, but it's definitely stronger than random, because you can just, random model just is oblivious of everything and just flips coins IID. So in this model, quite surprisingly, we can actually correct a deletion fraction tending to 1. Okay, non-explicitly, but we can show these codes exist. So at least it says that the answer, so the sum of oblivious is not going to shed much light maybe on the worst case thing, because the answer is different. It behaves more like random than like worst case, because worst case we know you can't exceed half. Another model we studied, which is the online model, where you say, the decision on the ith bit cannot depend on the future. So somehow you have to make your decision based on the past, which is a reasonable information theoretic model, or information theoretic restriction. And in this model, we got this result. Again, we thought, okay, can we correct? Maybe we can correct 1/2 in this model, and maybe that will shed some light. And we made some progress in this, depending on how we view it. We basically say the answer, whether you can get to half in this model, is the same as whether you can get to half in the worst case model. So maybe this gives you hope that adversarial is easy because you only have to tackle online model, but probably the truth is that it just means that online doesn't buy you much, and it's also.
I'm confused why oblivious is particularly stronger than random. I mean, maybe for efficiently, but otherwise, doesn't it seem that?
Well, you can have bursty patterns, right? So.
I mean, this is basically what you're saying is that the oblivious adversary should actually might as well just pick the set of none, right? The set of.
Well, no, it's actually, I wish I could say that. Actually, if you look at the construction, our construction has horrible rate. As p tends to 1, if p is like 1 minus epsilon, the rate of those guys is like epsilon or omega epsilon. Our rate is terrible. So.
But still, you might guess.
Might guess, yeah, I don't know. Yeah, so.
Would you guess that?
Would I guess that it's the same?
Yeah.
So in models like errors and erasures, indeed what you're saying is true. Oblivious basically does as well as random. Like it has the same capacity. So you can ask the same oblivious question for bit flips also, and then we know we can do as well as Shannon model. Though it's not, you have to read, it's not the same. The reason is not immediate, but that's the answer. But here I don't know this is the case. It could be the case, yeah. So we have only said what is the 0 rate regime. When does the rate hit 0? And you can go all the way up to 1. But whether this is actually harder than random, I don't know. But I suspect, if I have to bet, I would probably say I'll agree with you in the sense that maybe it should be more or less as good as random. Which is the case for other models I know, like erasures and errors. But deletions are a whole different beast, so I don't know. All right, so maybe I should finish now. Or?
Maybe briefly.
Okay, so in honor of Sergei, which is just one erasure, let me talk about this, because this is really, at MSR, I should at least talk about this, because, okay, so back to erasures, back to where we started the talk, okay, and this part is quick, and then I'll be done. You had ReedSolomon Codes where it had the optimal property. If you had any k symbols at the output, you could get all your original symbols, which is the best you can get. These are called MDS codes. And for this reason, these are very popular in storage. For example, you can use it in cloud storage, where you have k servers worth of data. You store it redundantly across n servers. And the great thing is that n minus k of these servers could completely crash, and all your data will still be safe. Okay. For example, at Facebook, I guess, these are some parameters used. So you can spread 10 symbols over 14, and you can tackle 4 server failures. Okay, all this is very classic. Why am I saying this? The point is one thing which is very common in distributed storage now, and Sergei knows a lot more about this than I do, so ask him for the practical connections, is that one server fails or becomes unavailable. So you would like to repair it, because you would like to maintain the system redundancy. So the question is, how can you efficiently repair this node? Okay. Now what you could do is that, well, nothing terrible has happened. You can get the full data from any k servers. Okay, so you can do this, but the point is it seems a bit wasteful, because if you go to k servers and read the data, you can actually recover the whole thing. But I only want this one piece of the data, one server worth of data. So the question is, can we do better? Because I'm not trying to recover the whole code word, I just want to know this particular failed server. Okay, and the answer is no, because for the exact reason these codes are very good, it turns out if you only look at k-1 servers, it gives you no information on the failed server. So if you look at k, you get everything. You look at k-1, you get nothing. You get zero information about this. So the answer is no. Okay, when the answer is no, you change the what you mean by better, and then you get the answer yes, right? So it's like, so what's the other thing you could look for? And by the way, this thing of how many servers you look at is this locality thing, which are underlies all. Now there are two bigger experts than I am in the audience now, since Parikshit walked in. So that's called locality. There you optimize for locality, and there these ReedSolomon codes are not going to buy you anything. But what else you can do? Another metric is that you say that, well, you contact a server, but maybe you don't download all of it. Okay? So maybe you download partial information from these servers and you combine them and you piece together your server. So in this model, what the metric becomes, what's the total amount of downloaded data? What's the total bandwidth? And then the question is, how many bits does the replacement node need to download? And this is exactly what the subject of regenerating codes address. Okay, it started in some work out of Berkeley and it's really exploded in the last 5-6 years. And there are lots of great constructions, lots of things are understood. But the point is, what about ReedSolomon codes itself? Okay. So here, if one symbol goes missing, you can again go and get the value at k other points, download all the things, and you'll get the answer. But that seems a bit wasteful because you're downloading, basically that suffices to recover all the data. Okay. Can you do anything better? And even though there are tailor-made codes which address this thing, it's still useful to address this because ReedSolomon codes are still used in practice, and it's a very basic code. So can we do something better than this traditional polynomial interpolation? Okay. Okay. Since I'm sort of low on time, let me just state one thing we prove, just to give a sample. So what we prove with Mary Wooters is the following: for a particular instantiation of ReedSolomon code, which is a very natural one, your field is size 2 to the t. You evaluate the polynomial at all the 2 to the t points, and let's say your k is n over 2, so your degree is n over 2. So in this case, the traditional scheme will say go to n over 2 points, download them, and then interpolate the polynomial. That has n log n bits of download. But what we can do in this case is that there is a repair scheme which just downloads 1 bit from the remaining servers and pieces together the data. Okay. So again, it's a degree n over 2 polynomial, and you want to know its value at 1 point, which has gone missing. So you can of course recover this by finding the value, querying the value at any n over 2 other points. But rather than doing that, what I'm going to do is I'm going to get 1 bit of information about its value at all the remaining points and use that to piece together the data.
And this involves node computation. So in order to produce a single bit.
Yes. So this involves node computation. This involves computation at both the node and the server. Node and the repairing mechanism. Yes. Yeah. Again, this is just it's just a fun theorem about polynomial interpolation. I don't know how much it will impact the storage motivation itself, but it's a nice algebraic fact. But one thing which is quite nice is that following up on this, Min Ye and Sasha Barg basically said that using the tools we developed to analyze ReedSolomon codes, they said there are actually ReedSolomon codes themselves which are basically as good as some other tailor-made codes in this framework. So in some sense, if you pick the evaluation points of ReedSolomon codes carefully, they can do the job in this world. Okay.
That means they meet the cut set bound.
They get very close to the cut set bound. Yeah. And I think now they basically meet it also. I haven't seen their more recent work. Okay, got close to it. Yeah. But yeah, the evaluation points are very goofy. I mean, they pick them carefully, and the subpacketization is huge. All those things. Okay, I think I should close. So again, coding theory has lots of old problems, and still many things we do not know. I guess the deletion question was a striking one. There are many other ones like that, and we made a lot of progress in many different settings using variety of techniques. And really for the talk, I handpicked a few models which I worked on, and in particular all these models are coming from a more communication storage angle. That's at least ostensibly the motivation for these. But there are many other models which are actually motivated by computer science, cryptography and complexity in particular. I've listed a few here, and there are also lots of work which has happened in these things, like locally correctable codes, non-malleable codes, and so on and so forth. Private information retrieval. Okay, so there are experts in the audience on all these things. And what's also cool is that there are also some new questions like this, correcting just one erasure. It seemed like a completely solved problem, right? What was new about that? But really there is something new and that came from demands in emerging technology, which is very nice. And there are many other such things as well. I talked about regenerating codes. I mentioned these locally recoverable codes, which were developed at Microsoft Research, and also some other things like flash memory codes, network coding, and so on. Okay, so there's lots of things going on in many different directions. Okay, so I'll stop there. Thanks.
Maybe I missed it, but did you tell us about how you go from the 1/3 to the root 2 minus
No,
1?
yeah, no, we don't.
Is it it's a different code?
No, it's the same framework. We just change these inner strings. So in these long runs of zeros and ones, we put some dirt of ones. So we call it the dirty construction, and this is the clean construction which I showed. Basically, in these long runs, we intersperse it with ones every now and then. And the relative proportion of that is carefully balanced to balance two trade-offs, and that's where the square root 2 points.
I mean, what's the intuition for why that's better at all?
What's the intuition for why that's better? Which is that if you have this long run of zeros, so if you, for example, it'll be a little tricky to explain without drawing the thing, but basically, let's see. Okay, maybe I'll give you an answer offline. I can give you more details. But basically, it increases the span. So in the worst case, span 3 can be increased. These dirts increase the span further, and that helps.
Well, that's great.